Welcome everyone to this DIEP seminar on the Physics Nobel Prize 2021. For those who don't know what DIEP is, I will say just a few words about it. So what is it? It's basically a research institute that tries to foster collaborations and perform research on the topic of emergence. Very concretely is collaboration between different institutes at the University of Amsterdam, Institute of Mathematics, Computer Science, Advanced Studies, Physics, Chemistry, and Logic. It started as a national endeavor via the Dutch science agenda, Route 2. It still has a national flavor, but at the moment is mostly clustered around Amsterdam. And research on emergence, for those who don't know, can be made a bit more concrete, and basically we try to understand how to begin with a microscopic system with different interactions and try to obtain a coarse-grained description at a different scale, at a larger scale, an emergent description, and how these two descriptions at micro and macro scales are related to each other. We organize different workshops, seminars, including this one, public lectures. We also have occasionally open positions. There's an education material. If you want to know more about it, you can visit the website here. And if you're wondering what is the relationship between all of this with the Physics Nobel Prize 2021, then that should be clear from one of Parisi's quotes. He said, "Most of my research has dealt with how simple behaviors give rise to complex collective behaviors." And that is basically almost a definition of what emergence is. And Parisi, but not only Parisi, but also Manabe and Hasselmann, they were masters in understanding this. And this sort of shines through the multiplicity of systems that their analysis actually applied to, including climate change, neurons, spin glasses, particle physics, flocking of birds and schools and of fish, etc. So they did a lot of work on this, and the purpose of this session is to highlight some of their contributions to science through the glasses of these different researchers who are aware of parts of their contributions. This is, of course, not all the contributions that they have made, but it should give a pretty good idea about what they are. And that being said, I would like to introduce the first speaker, John Madosh, who's an emeritus professor at University of Leiden. He has made numerous contributions to the physics of metals and spin glasses. In fact, I found this quote in one of Parisi's articles called The Discovery of Slowness, which says, "In the 70s, John Madosh and collaborators found the first good experimental evidence of a transition." Here, this transition refers to a glass transition. And in fact, John Madosh was one of the first to sort of experimentally measure this transition, and he was at the forefront of spin glass research when it started and began. So he has a lot of inside knowledge into this field, and he is going to present it. And I also would like to mention that he wrote a very nice book on spin glasses, an experimental introduction. And I really recommend people to read the first 3 chapters of this book if they want to have a flavor of what spin glasses is all about. It's extremely well written, so it's a really nice book. And without further ado, I would now pass on the word to John Madosh.
Okay, terrific. Got it? Got it here. Okay, I'm going to open this up a bit so we get the full screen here, and you can read what I'm going to attempt to do here.
Yes.
Try and give my viewpoint on why Giorgio Parisi got the Nobel Prize. And I'm going to focus upon something that Jay just mentioned, something that is very, very simple. And it has turned out to be so complex that I can't give a real good physical interpretation of it, despite Parisi's work. Let me begin with my conclusions because I'm going over time here. And so I want to say, why did Giorgio Parisi get the Nobel Prize? It's for his correct theory of replica symmetry breaking. And this, oops, what the video is coming in, good. And what he did, and this is statistical mechanics. We're back in the 1960s, the 1970s, and what we see there is that there is a tendency to move away from these equilibrium phase transitions, which they have studied so well with statistical mechanics, the critical phases, the critical exponents. They're looking at disordered systems. And when you move into disordered systems, you need to use this equation, which is called the replica trick. And let me put, whoops, now, okay, I want to get this back here. Oh, God. Okay, let me try again here. I'm trying to get a pointer to work here. The pointer is here. Okay, here's my pointer. So Parisi then described a method, a matrix block technique of order parameters. If you have a single order parameter, you can nicely describe all the phase transitions until then. However, Parisi's matrix block, his technique of expanding a matrix of order parameters to almost to infinity using recursion relationships, and then looking back with this replica trick, you have to take the limit of the replica going to 0. And when you do that, you get the strange result that the order parameter is a function of some interval. And this order parameter is continuous. It's a continuous function. So this broke open classical statistical mechanics. Today in the 2000s, we would be more interested in quantum statistical, but let me then go on and show you something that is very simple. If you look at what a spin glass is, and this was all of Parisi's work was applied in the mid-80s, the 1980s, with his collaboration with the French, it was applied to the spin glasses. There were papers coming out with collaborators on how you can then get the interpretation of his mathematical model and his matrix. Look at this. I have some spins. This is so simple. I have some spins in a gold matrix. Gold is non-magnetic. These are iron spins. And I look at the interactions. I neglect these ferromagnetic big clusters, which come into later theories. However, this spin here is a first nearest neighbor, and it's antiferromagnetically coupled. If I come down here or come down here, this nearest neighbor spin is ferromagnetically coupled. So I want to take this array, this random array of spins, which interact rather long distances. We have the mechanism, and these interact with a probability, depending on the distance, ferromagnetic parallel, antiferromagnetic antiparallel. And this freezes out. So when all these spins become locked in, become frozen at a rather well-defined transition, we have the frozen spin glass state. So we can now go on to, this is simple. This is, here we are in 1972, we published a paper with Vince Canella was my PhD student. We were working in New York, and we wanted to put the title in this physical review, which would be Spin Glass Transition, Spin Glass Magnetism. The editor refused to allow that to be in a title. Spin glass at that time was unheard of. It was not a valid concept of physics, condensed matter physics, in the 1992s. We were lucky we got it into the abstract, and we worked on it by showing with a susceptibility measurement that there was a sharp phase transition. was field dependent, was concentration dependent, was temperature dependent. A few years later, Edwards and Anderson came along with their theory of the first attempt to show that there is a phase transition in the spin glass in a complex magnetic system. And this then was improved by Conrad Fisher the same year. And then at the end of 1975, David Sherrington and Scott Kirkpatrick published a big paper which in detail did the calculations of the spin glass transition. Now it's amazing, this paper garnered 4,000 citations, right? And this paper then was shown a few years later to be wrong. However, in later time, Parisi was doing his mathematical modeling. In 1979, 1983, he published 2 single author papers on his matrix block to derive the order parameter of a spin glass. And this was the breakthrough work, which he then, with his colleagues at the École Normale in 1986, 87, 88, throughout the late 80s, he applied this to the spin glasses. And this was a very, very deliberate attempt to give it some sort of experimental contact, to give it some sort of interpretation. And this is still very difficult today. And I guess we all have our own interpretations because it's so complex. I'm going to omit all of these other references. There are many, many experimental references on the spin glasses, and particularly theory. There were probably well over 1,000 publications on the theory, on the various theoretical aspects of the spin glass. So we have these 4 simple key characteristics of a spin glass: the frequency dependence cuffs and the AC susceptibility, a difference between the field cool and zero field cool states, very, very different spin glass states, which depend on the order parameter that you measure with this type of field cooling. We are very lucky with the spin glasses. We have the congenitive field. This field is the tunable. We can tune all the behavior of the spin glass with a magnetic field, with its orientation, with its frequency, with its pulsing. So then we go on to the specific heat. There is non-critical behavior in a specific heat. However, at low temperatures, there is this unusual metastable state with remnances, with irreversibilities, and in particular with aging. If I let the system sit for 10 to the 4th or 10 to the 5 seconds, that's a week of time, I get that the system is constantly evolving. I need fine measurements to detect that, but it's constantly evolving. So why is this important? Simply because there are now 1,000 systems which are designated as good spin glasses. Let me not get too bogged down into this. All these systems have a magnetic component. So I'm saying the spin glass is a random magnetic system that has an indeedly complex phase transition. I could look at the quasi crystals, like high temperature superconductors, have a precursor to the field where the spin glass phase, and I can go through this with all the experiments that I showed and easily determine that these are good spin glasses. Okay, we want to go on now to the evolution of spin glass theory. As I said, Edwards and Anderson, then working in Cambridge, came up with an order parameter. This order parameter was, first of all, time dependent. I could use this even as a single side order parameter, like II, and look at, as the time goes on to infinity, this spin, this dot product remains finite. There is no mobility as I look on time. Now, in statistical mechanics, for ergodic systems, I can convert the time correlation function here into a thermal averaging squared function. for the order parameter. This is the proposed order parameter of Edwards and Anderson. I need to do a thermal averaging, and I need to do a configurational averaging. Edwards and Anderson then, using mean field, using the linear response, calculated the susceptibility, it's Curie-Weiss, and here in the numerator, there is the onset of this Q of T. At a certain temperature, Edwards and Anderson were able to show that there appears a Q of T rather sharply, and this is the famous cusp in susceptibility that we propagated before. So we go back now to the end of 1975. We have Sherrington and Kirkpatrick. Sherrington and Kirkpatrick used the Edwards and Anderson order parameter. It's a constant. This is a single order parameter, and they did a real detailed calculation of all the properties, all sorts of transformations of using this trick, the replica breaking trick. However, after this publication came out, and as I said, there was approaching 4,000 reference citations, everybody, experimentalists, it was very amenable to experimentalists to look at what they're saying, what their susceptibility, specific heat, and compare with their phase diagram. We were all enthusiastic about this. However, in the intervening years, until 5 years, many theorists began to look at this replica symmetry breaking scheme. And the conclusion, after much huffing and puffing, was it's incorrect. It gives unstable solutions for their spin glass state of infinitely interacting spins over the whole matrix. And so you had to then take this with a grain of salt. Perhaps you get some experimental insight. However, then Giorgio Parisi came along, 1979, the spontaneous replica symmetry breaking, where his order parameter is a function of this interval. This is an interval usually taken between 0 and 1, and this is a continuously variable. So if Q is a function of a continuous variable, it's infinite. The order parameter goes to infinity. And so there have been now numerous attempts into the 1980s, into the 1990s of a way of interpreting, a way of using this order parameter. And one of the ways is you look at the probability distribution of overlaps. You use the order parameter and you look at what that gives you. What is that significantly strong enough to give other order overlap with other order? How do these local order parameters differ? There have been numerous attempts from the theory side to do timescales. As we tried to do timescale measurement, we're able, now the experiments are coming out recently of somebody waiting 2 or 3 weeks at a constant temperature. Now, in 1986, the people at Nobel Laboratories, Fisher and Hughes, decided that they had an alternate approach to the spin glass problem. What they were going to do was to take a droplet. This droplet is an excitation out of the frozen spin glass state. So I have all the spins frozen and I create a droplet. And I want to see what the energy of that droplet costs. And there is a length scale of the droplet, there is the exchange interaction, and there are some critical exponents. Fisher and Hughes showed that if these critical exponents are of order, have this dimensionality, which gives greater than this exponent here, there is a spin glass instability. In other words, if I have some random changes in my droplet, the droplet expands and quenches the spin glass. You have a spin glass instability. So these theories then give different predictions. But first, okay, let me just look at what are these different predictions. Symmetry breaking says that there are many equilibrium states, probability distribution of overlap with the magnetization in a different state, and the replica symmetry breaking model predicts a spin glass phase transition at a magnetic field. When you apply a magnetic field, there is a spin glass. Daniel Fisher and David Hughes say no, the application of a magnetic field quenches then the spin glass state. It destroys the phase of the spin glass. So we now have a way to do experiment or even do large-scale computer simulation. So I want to get into the order parameter, remembering ferromagnetism, simple two minimum free energy at a given magnetization. And what I can do here is just say that at this temperature below the Curie temperature, I have an equilibrium ground state. I have the system locked in this. This is my ferromagnetic transition. I could do all the critical phenomenon. I could look for all the excitations, the spin waves, and so. And also, which is very important in today's work, I can multiply this by an exponent, an e to the I q dot r, q being the Néel vector for antiferromagnetism, r being the Bravais lattice vector of my given crystal structure, which supports the antiferromagnetism. So I would move another axis out here, which is the q value. Q is 0 for a ferromagnet, but I would look at a Q100, which is just an up-down antiferromagnet. So I could put all antiferromagnetism, all ferromagnetism into the simple equilibrium minimum phase diagram. Now, here we go over to what Parisi is saying. What is coming out of Parisi's theory of an infinite number of order parameters is this type of formation of a multi-valley landscape. This is the key interpretation. This is coarse-grained schematic here. But even in these valleys, which represent frozen-in states, there are mini valleys. And the system can still fluctuate around these mini valleys. And finally, if I go to very, very low temperatures, I get a bunch of these valleys which lock the spin glass into. So in order to get a physical interpretation of this multi-valley landscape, this immediately generates from the infinite number of order parameters. This immediately comes out of Parisi theory. The breaking of replica symmetry requires this. I can look at a single valley here. I see the mini valleys. My system is fluctuating around here. I get some time delays, even at low temperatures. I get the slow dynamics. And if what I need to do then is to look at the overlap of these valleys, if I get a distribution of overlaps of these valleys, I am generating then the equilibrium state of the spin glass. If I sit in a single valley and look at the behavior of a single valley, I'm using effectively the single value Edward Anderson order parameter, which is a short time scale replica. So this is what we are getting now. And let me then finally ask the question, since I'm running out of time. The mean field theory predicts, famous Dell'Almeida-Fowlis line, that there is a phase transition, which is ergodic paramagnetic, non-ergodic spin glass. And so if we jump on to the next slide, is there an AT line? This is what we experiments are looking at. The two theories are radically different here. There is the phase transition model of Parisi, and there is then the non-crossover, a smearing out. There's no spin glass phase in a magnetic field, a tiny field. If I look at the experiments today, I see that there is more recent experiment and simulation data, simulation conclusions that it's this type, it's this A instead of the B. So this is an added indication for the validity of the replica symmetry. To conclude now, here is what we got with the spin-off. None of these are magnetic systems. I removed the 1,000 systems of magnetism and I look at now what happens. I can use the spin glass, the random, the competing, the frustrations, the rough landscape. I can use this all to do things like the biomolecules, superconducting glasses, stock market evaluation. People are now playing with hedge funds using spin glass-like theory to evaluate the sort of flexibility and the permanence of various stocks. They could go on to social networking. So if you're probably looking for a new partner and you want to improve your dating, you would use the theory of this replica theory. Finally, the exchange bias is a hot topic for me, and it means that exchange bias is used in all the computer chips. It's an anti-ferromagnet being biased with a ferromagnet, and you improve the displaced hysteresis, the distorted hysteresis loop by putting a spin glass. So let me stop and let me thank you. And this is my overview, unfortunately too short and too cursory, of the spin glass. So I'm finished. Thank you again.
Thank you very much. Thanks a lot for this very nice presentation. We have time for some questions if anyone has something would like to ask. If you do, just you can just unmute and speak or raise your hand.
Perhaps I have a bit of a stupid question. Hi, John, how are you doing?
Hi.
In a way, I get the impression from your talk, right, that it's still not completely watertight, settled that the replica work, right? So is there an issue with the Nobel Prize? I mean, you know, you get the Nobel Prize when it's really rock solid. There's no doubt left. How would you assess that?
Yeah, yeah, this is my point of view. As I said in the beginning, he had to wait 40 years for this Nobel Prize. The topic in the 1980s was hot. We were also into the running with our experiments. It was very, very hot. And then it was put on the shelf. And so you have to ask the committee in Stockholm why they took this out of the refrigerator or out of the shelf to give Giorgio Parisi his Nobel Prize in 2021. Immediately, he deserves it. And I'm being unfair, admittedly. I'm neglecting his many other contributions to real glasses, to fluctuate, even to particle physics that was preceding his work here on this. However, because of the enormousness of the spin glass and the spin-offs of the spin glass, I feel he deserves the Nobel Prize for breaking this up. Even Anderson got a in his Gesamtwerk, or his Nobel Prize, there was a sentence about spin glasses in it, but that was for his complete, his oeuvre, and not for specific. I think more the Nobel Prize of Parisi was focused on the spin glass. The Nobel Committee they were showing all these slides of the spin glass, and they were focusing with the public and with the press. This appeared in the New York Times, the spin glass sketch. So this is the popularity of the spin glasses.
Still, right? I think you rightfully highlighted the replica trick, right? That's really that.
Yes.
But you know, to illustrate the uneasiness, right? I guess the latest success of it is the Suchav-Yeki-Tayev model, right? That thing that is right now raging also in the string theory community. And I know from Suchav himself that he actually delayed the publication for a year because it's relying on the replica trick, and he didn't trust it.
Mm-hmm.
And much later, it turned out, right, that in this context, replica tricks are impeccable, right? They do exactly what they should do. But, you know, there is all the time this lingering doubt. It's a very weird trick, and you never know, right?
Yeah. So what can we do?
Yeah.
It's still there hasn't too much theoretical contribution. Okay, these are still open questions. I would look at it not from the theoretical. I look at the material wise. I look at it that we have 1,000 different materials, which somehow can be fit in to get some understanding via this replica trick. Okay.
Does anyone have any more questions? Well, I have one, if I may. What do you think is the major open problem in spin glasses right now?
Okay, I would go back a few slides to absolutely show it's difficult experimentation to test this Del Almeida-Thales line. Perhaps large-scale computer simulations. There should be better experimental tests looking very hard at the sort of interpretations of the Parisi theory. There is a number of experimental work. There are people, guys, particularly in Texas, who spend 2 or 3 weeks just looking at a tiny decay of the spin glass and trying to relate it to some sort of aging model, which probably then goes back to the replica symmetry breaking and the distorted material. So this, of course, would have to be combined with theory. Theory today is also there are this big multiple process computer. There's a consortium between Paris, Madrid, and Rome, where these big computers are running on spin glasses. So perhaps this gives new information.
Okay, thank you very much.
You
can unmute and thank John again. Now we have Idan. Share.
Yeah, can you see my screen?
Yeah, let me see. Yes, it works. So Idan is an associate professor at the University of Amsterdam. He has made numerous contributions to the understanding of glasses and its properties, as well as soft matter systems and many other things. And he's going to speak about the glassy state of matter. Please go ahead.
Yeah, thanks, Jay. Thanks, John, for the historical review. So I'm going to talk about maybe less well-known work of Parisi and collaborators that has to do with understanding structural glasses. And the work has been done for the hard sphere model, the hard sphere liquid, and the hard sphere glasses. And so let me just continue. So I guess that's the audience doesn't know me. So I am a member of the DIEP in Amsterdam since 2014, and my research focus is on understanding the statistical micromechanics of this sort of materials. And just to give you a taste of the type of science that I do, here's an example of an analysis of a model computer glass. And what I'm showing here is the map of the spatial map of the specific heat of this glass. And what you can see is that there are red and black contributions that come from the various interactions between underlying particles in this 2D system. And you can see that there are these excitations that are localized that carry most of the heat capacity of the system. We all know that equipartition should normally hold and that every normal mode contributes kBT. But the spatial arrangement of the contribution is something that kind of highlights the defects and the excitations in the glass. I was also busy studying the statistical properties of these fields. And so this is why Pulisi's work is also highly related to what I do. Okay, so I'm going to talk about Pulisi's work in the context of two most fundamental problems in the physics of glasses. One of them is the process of glass formation and the way that the viscosity of supercooled liquids grows as the temperature is decreased. And the other is the problem of jamming, which occurs both in thermal and athermal systems when they are compressed or decompressed. Here I'm showing you a picture from the experiments in the Van Hecke lab in Leiden, where you see an emulsion being compressed. And this is a phenomenon where rigidity emerges once these droplets start to overlap with each other. And it turns out that both of these phenomena occur in the canonical hard sphere model that I am just spelling out here. What you assume is that you have hard spheres that have all the same size diameter sigma, and the potential is infinite if they overlap and zero otherwise. In this system, the key control parameter is the packing fraction, which is simply the volume occupied by the particles divided by the total volume of the system. So what are the big problems in glass formation? If you look at the viscosity, this on the y-axis, these are experimental data of the viscosity versus temperature for various types of liquids. What you see is that the viscosity grows by several orders of magnitude upon reducing the temperature. The way that the viscosity of these materials change, it changes between different materials. There is the kind of the generic way of representing these data is plotting them against the inverse of the temperature, where the characteristic scale is the glass transition temperature, which is just an arbitrary scale that is set by requiring that the viscosity at the glass transition temperature is 10 to the 12 Pascal second. When you do this, what you find is that some of the materials, like silica, they follow a straight line, indicating what we know as an Arrhenius activation rate. But some other materials, such as OTP, they have a very curved kind of shape when represented in this way. And this kind of differences between these different liquids gave rise to this big question about glass formation, is whether the dynamics of fragile glass formers, the ones that are non-Arrhenius and don't obey this straight line in this kind of representation, are they controlled by an underlying thermodynamic criticality? And this idea was also inspired by results from spin glasses, as we heard just now from John. Another piece of evidence that kind of drove a lot of the interest in this field was observations done already more than 70 years ago by Kausman, who looked at what is known as the configurational entropy of these various liquids. And what you see is that the configurational entropy is essentially the entropy subtracting the vibrational contribution to the entropy. And what you see is that some of the fragile liquids, if you plot this observable as a function of the temperature, then you see that it seems to extrapolate to zero at a finite temperature. And this was one of the big questions or the big mysteries that came out of experiments on liquids and glasses. How is it possible that the configurational entropy vanishes at a finite temperature? It cannot become lower than the crystal entropy. So that is about glass formation. Now I'm going to jump to the jamming problem. So again, consider your canonical hard sphere system. And kind of the hallmark phenomena that takes place in these kind of systems when they're compressed is that the ratio of the shear to the compression rigidity vanishes at the critical packing fraction with some power law. There is a diverging correlation length that happens at that transition that diverges at this critical packing fraction phi c. And another quite remarkable phenomenon that takes place is that if you count the number of interactions, if you want the number of pairs of particles that are bouncing onto each other, that number approaches 2 times the spatial dimension exactly at the critical packing fraction phi c. On top of that, if you consider the properties of the critical state that you reach by taking this hard sphere packing and just compressing it until you cannot compress it further, then what emerges is that if you look at the statistics of the forces between these particles, then they also are described by a distribution that grows as f to the theta with theta some non-trivial exponent. So this is in a nutshell the phenomenology of jamming. So the work that I'm going to discuss has been published between 2012 and 2014. And as you see, Parisi has been a driving force in all this work, but I also want to highlight the contribution by the other very good scientists that worked together with Parisi on this, Jorge Kulchan, and also Francesco Zamponi and Pier Francesco Urbani. Both those two last scientists were actually PhD students, with Giorgio being their advisor, their mentor. So actually, in these workers, they obtain the exact solution for the behavior of hard spheres in infinite dimensions. And this was done, as mentioned by John, using the replica trick, where the order parameter would be the overlap between different replicas of the system. So I'm not going to go into the details of the calculation, but I want to show what are the results. And so the main result is a unified phase diagram, both for the glass transition and for jamming. And I'm going to walk you through it as slowly as I can. So on the y-axis, we have the inverse of the pressure. And on the x-axis, we have essentially the packing fraction scaled in a way that has a well-defined limit in the limit of infinite dimensions. So this is the equation of state for the equilibrium liquid. And then as the system is compressed, there's a glass transition that takes place at a packing fraction that is called phi d. And it has been resolved that the viscosity diverges with the true singularity at this packing fraction phi d, and the exponent also has been calculated from the theory, indeed numerically, but nevertheless to the precision allowed by the numerics. And what happens at this glass transition is indeed a replica symmetry breaking transition, where if you think about the phase space of the liquid, then of course it's ergodic and it can go to all of the states. But once you cross this glass transition state, the phase space is broken into regions that are actually not accessible dynamically, because the free energy barriers between any two of these basins are infinite in the thermodynamic limit. So you have a partition of configuration space into different basins that are not connected, but nevertheless, the calculation can still be extrapolated into this glassy state, which is the equilibrium, and it's not exactly equilibrium because it's not ergodic. However, if you do your equilibrium reweighting of these different basins, then you can extract the equation of state also in the glass phase. Okay, if you start from the glass transition equilibrium state and make an infinitely fast compression of your system, then you arrive at some point here, which if you want is the random loose packing. It's the most dilute but jam state that you can achieve with hard spheres. And then from that point, so this is the point where the pressure is singular, because the temperature in this system is assumed to be constant and the particles are rattling in their cages. Once you compress it, then the pressure explodes, goes to infinity, and then you have a jamming line that extends from that random loose packing and onwards. At this line, also, no matter how you arrive at this line, if you start from the equilibrium glass transition or deeper in the equilibrium non-ergodic glass, you would always arrive at the jamming line when the number of contacts approaches exactly 2 times the spatial dimension. From the equilibrium glass transition point, there extends a Gardner transition line. Above it, the phase is known as a stable glass, whereas below it, it's known as a marginal glass. So if you were to cross this Gardner transition line, what would happen is what is described here. You start from your stable glass state, is what I said before. What happens at the glass transition is that the configuration space splits into different basins. But then as you cross the Gardner transition, the free energy landscape becomes fractile, and each one of these basins is then further partitioned into sub-basins, which are embedded in sub-basins, et cetera, in an infinite hierarchy. And that is what is known as the full replica symmetry breaking line. So this is the phase diagram. And if you think about the dynamics, how are they manifested in real space? So if you look at the mean square displacement of particles, in the liquid state, we know how it behaves. You have a ballistic regime, and it's followed by a diffusive regime, and you have ergodicity, etc. But once you cross the glass transition packing fraction in infinite dimensions, then this partition of the configuration space into these basins implies that, of course, dynamics are going to be arrested because each system is locked into one of these basins, and then the mean square displacement just has a plateau and you would never find normal diffusion. Then if you were to continue to compress the system, you would undergo again the Gardner transition, right? You would cross the full replica symmetry breaking line. And in that case, indeed, as John mentioned, for the spin glasses, you find the phenomena that the system doesn't have a well-defined reference state around which the particles fluctuate. They are indeed caged and diffusion is inhibited. Nevertheless, the mean position of these particles is constantly changing because of the frustration and the marginal stability of the state. And that's why if you looked at the mean square displacement, you find that it would slowly age in a logarithmic fashion. If you think about the contacts formed between the particles due to the fractality of the free energy landscape, then what will happen is that if you run the system in the Gardner phase, you let it evolve, and then you do a crunch. That means that you just compress the system very quickly, and then you look at the identity of the contacts that are formed at the isostatic state, at the jam state that you can no longer compress further. And what you would find is that when you're in the Gardner state, in the fractal free energy landscape, then the identity of the contacts that you form at the jam state are each time going to be different. Whereas if you have not yet reached that state, then the set of interactions, even though the system is in the glass and it doesn't diffuse, then it will fluctuate around one well-defined inherent structure. All right, so going back to the results, the theory predicts that the distribution of contact forces, as I mentioned before, at the jam state goes like F to the theta with the non-trivial theta that they could calculate from the theory but using numerical solutions of the equation. And actually, a year before this prediction came out, which was in 2014, together with collaborators, I have calculated the distribution of contact forces in 3D packings of hard spheres. And I found an exponent 0.44, which is reasonably close to the prediction for the infinite dimension jam states. And we're very happy to see that there is a theoretical explanation for the exponent that we measured. Measuring this exponent is not trivial because there are essentially two classes of contacts that carry low forces. I won't go into the details, but there's a reason that it took a long time to be able to measure this in simulations. On top of that, the theory predicts that the distribution of gaps between particles that are not touching, the gap is denoted here by h, grows like h to the alpha with some exponent alpha that's also calculated numerically up to 5th digit by the theory. And in the same work that I discussed before, we, by a scaling argument, relying on marginal stability, relying on the fact that any kick to the system would destabilize it and cause avalanches, then we predicted that there should be a relation between the exponents theta and alpha. Actually, I'm missing a minus sign here. And it turned out, once the theory came out and these exponents were calculated, that the scaling relation that we proposed was satisfied up to 5th digit. So the theory itself does not predict the scaling relation. You can argue for it by marginal stability arguments. However, the exponents that are extracted agree with it perfectly. So since this theory of the exact theory of hard sphere thermodynamics came out, there were many attempts, both in experiments and in simulations, to validate whether this Gardner transition exists and is controlling the behavior of fragile glasses. Also the question of whether glasses as we know them, structural glasses from experimental glasses or laboratory glasses, are they in this Gardner phase? And so here I'm just showing a small collection of papers that came, this is 2016, 17, 18, and 19. And there are a lot of attempts to try to validate, both in simulation and experiments, whether or not some of this phenomenology carries over to finite dimensional glass. And I think that the consensus at this point is that hard sphere glasses do exhibit very distinct Gardner-like features. However, generic glasses, if you want as an example or a simple model like dense soft spheres, they don't show Gardner-like features. And so here is where I am my review of Pulisi's work, and I'm happy to take any questions. And thanks for your attention.
Mm-hmm.
Thank you very much, Ivan. Does anyone have any questions? Yeah, Vladimir, go ahead.
Hello, thank you. Very, very nice talk, as well as the talk of the first speaker. My question is a bit more general and also could be asked to first speaker as well. If you could please go to the formula of replica trick, so the basic formula of the discussion. Okay, thank you. So if we take a look to this formula, from the left hand side we have a log partition function, and from the right hand side we have some approximation of logarithm. And this approximation depends on parameter n. When parameter n goes to 0, this goes to logarithm of z. Is there any work, if you are aware, on where another kind of approximation is used. For example, if we go z to the power of n square minus 1 over n square, this will also go to logarithm, right? So if we change the approximation on the right hand side, will we be able to rederive new theory?
The idea is that z to the n represents the partition function of the replica systems. So I think that if you substitute this with something else, then I don't know if that's still represented, but I'm not aware of that. Those kind of things. Maybe John knows.
So we approve this approximation from like physical reasons, that we say that replica system can be formed only if we put z to the power of n. We cannot form some kind of generalized replica theory. There are no such work, there are no such or this is not meaningful.
I couldn't say that. I am not aware.
So I can answer the question. So first of all, what's on the right-hand side is not an approximation, is a limit, is a different concept. Second, if you call n, you call it n squared, then you have to change the denominator as well to n squared. And therefore, you are taking the limit of n squared that goes to 0. It's exactly the same expression.
Okay, thank you.
Does anyone have any more questions? Well, I have one, if I may. So the large T limit you have there, you mentioned that these works at the end were trying to verify whether or not these things are there. So can you actually use Parisi's work to try to refine the limit? Have 1 over D corrections or something that could maybe give you an impression of what it is at finite D?
Yeah, those efforts are obviously being made, but I don't think that there is a strict conclusion at this moment.
So he cannot get the Nobel Prize for this thing.
Well, I think that the fact that some of the results carry to finite dimension is a huge success. So, yeah, but whether it's relevant for laboratory glasses is still debated.
Are there any more questions? Or? No? Okay, then we thank Idan again. Yeah, we're a little bit behind schedule, but we just reconvene at 7 minutes past 12, so we have a little break now. Okay, yeah, I think we can start at least 7 minutes past 12. So I think people should be around now. So it's a pleasure to continue this session now with Elisabetta Palanti, who's a professor at the University of Groningen and has made numerous contributions to particle physics, phenomenology, lattice field theory, lattice QCD, and conformal field theory, among many other things. And she's going to talk about Giorgio Parisi, the School of Rome, and particle physics. Please go ahead.
Thank you, Jay. Thanks for the invitation. It is actually a pleasure to talk about the work of Giorgio. And I'm going quite back in time because especially in this case, I'm focusing on his work on particle physics. But as you see in this slide, there is also a little bit of spin glasses, you probably recognize. And the psychedelic picture on top is a sort of an artistic impression of the interior of a proton. There are quarks and gluons floating around. There are many colors, but actually there are 3 colors in their interactions. Well, I have to do. What happens? Yes. Okay, so the motivation for the Nobel to Parisi in physics. Now, there was already some discussion before, and I would say, in any case, what is certainly true is that it is a recognition to a polyhedric nature of his scientific research. It reads, let me read it, for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. In some sense, it is also a recognition to an extremely prolific career. And I would not forget also, because I heard many other inputs also about what motivations could have been there. Also some more recent work on the impact of fluctuations also on climate modeling. And this is work done with some Roman colleagues, Vulpiani, Benzi, and essentially other collaborators. So I go back to this polyhedric aspect of his scientific research, and in this nature that goes, I would say now, not only from atoms to planetary scales, but I would say from elementary particles to planets. And in that nature, I would recognize also a common imprint, and that is the imprint of the School of Rome, that had always a broad but also rigorous perspective on any scientific problem. And to that perspective, Parisi added I would say a sui generis, a quite exceptional intuition for the correct solution. Now, this is the entrance of the School of Rome. This is the old department, the oldest of two departments of physics, of two buildings for the Department of Physics. It is entitled to Guglielmo Marconi. This is the place where Parisi works after transferring from Rome 2 to Rome 1 many years ago. This is also the place that looks very familiar to me because I studied there. And I literally spent a few years of my life there. I never seen the entrance of this building so empty, except maybe deep in the night. And in fact, a few days after the announcement of the Nobel Prize, this was on 20 October, you see the same place is pretty much crowded. Now, what is the reason? It's a festive occasion. And here you see Parisi with other people. Among them is also the head of the current head of the physics department. And Parisi is making a toast. And the toast is for his, for his maestro, his mentor, Nicola Cabibbo. He was, and in particular there they are, you see they are showing a new plate that is entitled to Cabibbo in front of the physics building. Now for Parisi, Nicola Cabibbo played a very important role, and Cabibbo was an exceptional exponent of the School of Rome. The School of Rome started, of course, with the Boys of Via Panisperna. You all know the movies, but also it was a fascinating historical moment for particle physics and also nuclear physics at the time with Fermi and his pupils. But it continued and actually flourished also in the post-war period with Amaldi. And Amaldi was the person, was the founder of the INFN, the national, the Institute for Nuclear Physics in Italy, and he was one of the protagonists for the startup of CERN. And what he had in particular was a very long-term vision that also included connections to industry. And after Amaldi, Cabibbo was one of the most significant exponents of the School of Rome. It continued, and later on, Parisi and the other pupils of Cabibbo continued with an extremely prolific work. So we are going back now to 1977. And this is also, let's say, just a bit before the moment in which Parisi is also becoming very productive in the theory of spin glasses. And back in 77, you know probably the Altarelli-Parisi equation. This is an evolution equation. However, at the moment, Altarelli and Parisi are both pupils of Cabibbo, and they're both in France at two different institutes, and they formulate these equations. Of course, the story is much more complicated and involves more protagonists. In fact, it starts with Gribov and Lipatov at the beginning of the 70s, who, however, did not address the complete problem. The real thing is quantum chromodynamics, the theory for strong interactions. But they reached a very significant understanding of a field theoretical description for particles. In 77, in parallel, Altarelli, Parisi, and Dokshizer, on the other hand, they solve the complete real thing, so QCD, and they formulate an equation that includes also gluons. Now, why this parton evolution equations, which is nowadays known as DIEP parton evolution equation, why it is so important? Well, first of all, what are partons? Now, a parton is a constituent of the proton. So they afterwards they were understood to be quarks and gluons. Now, the parton model was actually formulated by Feynman in 1969, so just a little bit before the works of Gribov and Lipatov. And immediately Bjorken, also together with Feynman, they used and they applied the parton model. The idea is that the proton is not elementary, but is made of constituents, the partons, and these constituents are almost free particles. And actually turned out that they had spin 1/2. This in the first understanding. Then this brought immediately to what is known as Bjorken scaling, that establishes the fact that they are practically free particles. On the other hand, immediately after, there was theoretical development that said that in reality there should be violations of Bjorken scaling. And so one of the ingredients to understand quantitatively how this happens are precisely the DIEP parton evolution equation. So here I write an expression that is in sort of a matrix form. It is, you can think of them as a renormalization group equation. That is an integral differential equation, and it tells you essentially how quarks and gluons distribute themselves in terms of momenta inside the proton. Where Q square, in this case, this is the exchanged energy, so it's the released energy, so the energy that is carried by a photon, a virtual photon that scatters onto the proton. And of course, this led to many other developments and a complete theoretical understanding of deep inelastic scattering of electrons onto protons. Another aspect that I think is ubiquitous in Parisi's work is the combination of analytical and numerical tools. That is certainly the case and in particle physics, but also later on in spin glasses. And by the way, if I go back, let me recall that here you see there is an imprint, which is the probabilistic view. So statistical mechanics here is very much present also in these early works of Parisi, and the idea and the probabilistic description of the system, which in this case is just the elementary constituents of a proton. Now, concerning the combination of analytical and numerical tools, I now tell you a bit of a story, a sort of an adventure that happened in those times that I think that influenced a lot also the attitude of Parisi towards computational work. This is the APE adventure. Now, the APE adventure, what is APE? APE is the array, stands for Array Processor Experiment. And this is really an adventure that started in 1984. A group of people in Rome, guided by Cabibbo, and Parisi was one of the young people also leading this initiative. With a lot of ideas. They actually, behind a beer in a brewery in Geneva, they decided that really they needed to go for the construction of a new supercomputer. Why? Because they needed a cheap and at the same time powerful supercomputer targeted for the simulation and the numerical solution of gauge theories. At the time, only Cray was available, and Cray is a vector machine. It was absolutely not appropriate for the simulation of gauge field theories. Therefore, they went for a so-called parallel machine construction. And here you see the first prototype for processors, homemade, in 1986, so just 2 years after. And actually, this little supercomputer actually climbed up immediately. And actually, between 86 and 88, here you see the flops in terms of teraflops, the power of the different supercomputers worldwide. And from 86 to 88, it was actually the fastest supercomputer in the world. Later on, there were the subsequent versions, so APE 100, you see, and APE 1000. They had their moments of glory because they climbed up also as fast as supercomputers. And then later on, after the 2000, APE Next sees a sort of a change of paradigm. Now it becomes really a commercial production where theoreticians by now are really decoupled from these enterprise. Now, remember that the years before that I mentioned, so the years 84, 86, these are already years where Parisi had already formulated a lot of the theory of spin glasses. He started to make contributions to the theory of spin glasses, as we've seen in the previous talks. In 79 is his work on mean field theory, for spin glasses, and this is just 2 years after his work with Altarelli on the Parton evolution equations. And later on, of course, I would then conclude that both numerical and analytical ingredients went hand in hand in his future work, continuing in spin glasses. And for example, in 87, he published the book that is by now a classic. It's a very nice book, together with two of his main collaborators at the time. This was Marc Mézard in Paris, and importantly, Miguel Virasoro, an excellent mathematical physicist who was at the time in Rome 1, while Parisi at the time was in Rome 2. And they together wrote this book, Spin Glass Theory and Beyond, which has a very nice structure. So it has a set of chapters and then a collection of reprints of the, let's say, the essential articles of the time. And by now, I think it's a classic for everybody that is working on spin glass theory or glasses. So I conclude here, and thank you for your attention.
Thanks a lot for this nice talk. Does anyone have any questions?
Oh, I stopped the sharing, sorry.
No, I don't see, but yeah, I can definitely ask one. So did he pursue particle physics further afterwards, or this changing to spin glass was just too much?
I think you see also in his work, in his initial work, there is also an imprint that is really statistical mechanics. So he had, I would say that after the Altarelli-Parisi equation and after the experience, so until the 86 somehow, where he was working also very actively on the APE supercomputer. And then after that, he focused completely on spin glasses. That is what I know and what I see. So after that, he focused on spin glasses. Yeah. But there was a period in which he continued to produce also in lattice field theory, together with other collaborators, but then he focused really on spin glasses and later on also on flocking and other, yeah.
Thanks. Does anyone have any other question? I don't see. So in due of time, then we thank Elisabeth again.
Thank you.
So now we have Luca. Luca, I'm going to give you sharing rights here.
Do you see my screen?
Yeah, just 1 second. Yes, it's in full. Yeah, it's full. So Luca Giomi is an associate professor at the University of Leiden. He has made numerous contributions to soft matter, biophysics, and also has worked on many theories of flocking. And now he's going to speak about from field theory to field studies, Parisi's view on flocking. Please go ahead.
Yeah, so thank you, Jay, and good morning, or actually good afternoon, everybody. So indeed, like Elena Palanti, I'm also somewhat related. I also studied in Rome, and I'm even somewhat related with Parisi, which I would like to represent as this ultramatic tree, which is an important part of the famous spin glass solution. So this is Parisi, this is Enzo Marinari, who's one of the students of Parisi, and I was one of the students of Enzo Marinari. So I'm connected with two steps replica symmetry breaking from Parisi itself. Now, aside from the joke, I was in the same group. So I went to several group meetings, and when I was a master's student in 2004, this was the main focus of the work of the group. This is well represented by this paper about spin glass complexity. Here, the idea is to compute the configurational entropy, the same quantity that Eden was talking about in spin glasses, and characterize the energy landscape of spin glasses. And the way to do it, the way they were doing it, was by mapping the problem of spin glasses into a problem that involves supersymmetry. So using supersymmetry to map two different field theories with different properties. I'm giving this little digression because I want to stress that that's another very interesting idea that Parisi put forward back in 1979 in this monumental paper together with Nicolas Surlat. The paper here is not about spin glasses, it's about another disordered system called the random field Ising model. And in this paper, Parisi and Surlat demonstrated that under some assumptions, this model can be mapped via supersymmetry to a Ising model without external field, but in -2 dimensions. And this is, again, another typical feature of Parisi's work, which, again, borrowing from the previous speaker, I would call psychedelic. So this was the focus of the discussion when I was a master's student. So you can imagine that, I was extremely surprised when a few years later, in 2007, I saw this paper. This paper is not a theoretical paper. This paper is an experimental paper. In fact, it's even more than that. It is a field study. So they literally went outside and filmed animals with the purpose of deciphering the way they move and they interact. I'd like to stress that among the authors of this paper, which is listed in alphabetical order, so the first author is Michele Ballerini, was one of my best friends as a master and an expert of electronics. And, you know, next to Michele is Nicola Cabibbo himself, okay, because Cabibbo was also an expert of electronics and a very passionate, lovers of electronic circuits. And together with Michele, they took care of the electronics for this work. Now, in order to appreciate how groundbreaking this was, I think it's useful to review a little bit the history of the physics of flocking, okay, which is started a decade earlier, and as an offspring somehow of non-equilibrium statistical physics. So first of all, by flocking or swarming or schooling, depending on the type of animals that we're talking about, what we mean is the fact that a number of similarly sized individuals can move coherently in space and time, even though there is no central control mechanism. So when you see a flock of birds, for instance, in the sky, this flock is very coordinated, okay? And nevertheless, there is no such a thing as a master bird that tells everybody else where to move. Okay, so it's an emergent phenomenon, and it's an emergent phenomenon which is dramatically different from equilibrium emergent phenomena such as phase transitions. The physics of flocking somehow started around the 90s when Tamas Vicek, a Hungarian statistical physicist, proposed a very famous model which in a way started the whole field of active matter that you may have heard of. As a matter of fact, the model of Vicek was inspired by the previous work of this man here. His name is Craig Reynolds, who's a computer scientist. And Reynolds was really trying to find an algorithm to mimic flocks in a realistic way for computer graphics applications, so like video games and animated movies. And the method is actually very simple. The idea is very simple. So in this algorithm, each bird is represented by a point, which is characterized by a position and a direction of motion. The model is two-dimensional, so the position can be described with two numbers, the x and y coordinate, and the direction of motion with a single coordinate, which is called theta in this equation. Time is discretized, and the position of the birds is updated using this simple rule. So the position at time t plus 1 is equal to the position at time t plus a displacement along the direction of motion of unit step. On the other hand, the orientation is updated in a following way. Each bird looks around a range, okay, range of interaction, which we call RC, finds all the birds inside this range, and then compute the average orientation of all the birds within the range. And then in the next time step, the central bird adapts its own orientation to the average orientation of all the birds within this neighborhood, okay, plus some noise to make the model stochastic. So it's a very simple model, and it's a model where the interaction between the birds is purely orientational and depends exclusively upon the distance. So this is what we call a metric interaction, okay, because it depends on the distance of the bird from a given central bird. Nevertheless, shortly after this model, it's clearly all kinds of variants came out, including variants in which the interaction is instead topological. So in this case, the range of interaction is not fixed, but each bird interacts with a given number of neighbors. So in this example, this number is 6, okay? Regardless of where these neighbors are located. They can be 1 meter from the central bird, they can be 1 kilometer from the central bird, it doesn't matter as long as they are their neighbors. So these two numbers here are important, and as you will see, they will show up again in the future. So let's give them a name. We call this the metric range, so the maximal range of interaction in this metric scenario. And we call this instead the topological range, the maximum number of birds, of neighbors a bird interact with in the topological scenario. Now, a curiosity that you will not hear in talks about floxing, but I'll tell it to you because somehow I followed the whole story more or less, is that neither Reynolds nor Vicek were actually interested in flocking. We're not interested in collective animal behavior. Reynolds was interested in computer graphics, and Vicek was interested in phase transitions. Okay. Nevertheless, the people who came after them, they really try to use the Vicek model in order to describe collective motion in real animals. One of the most successful of these people is Ian Cousin, who's currently the director of the Max Planck Institute for Collective Animal Behavior in Constance, Germany. And in this paper, which is very cited, highly cited, Cousin realized that in order to apply the Vicek model, for instance, to fish, to describe the school of fish, he had to modify it in a very complicated way, okay? For instance, by splitting this interaction range, okay, this metric range, into a set of different layers, in such a way, in each layer, the interaction is different. So for instance, there is, a layer where the interaction is positional and attractive, a layer when the interaction is positional and repulsive, an orientational interaction range. There is also a range in which there is no interaction that corresponds to a blind spot. So this is a complicated model. Of course, we're talking about complicated objects such as animal, but nevertheless, in physics, when the model becomes too convoluted, it's a good idea to look back at reality and perhaps try to do some experiment. And this is what the group of Parisi did. In this beautiful paper of 2002, which is extremely cited. Let's read together the first sentences of the abstract. Numerical models indicate that the collective animal behavior might emerge from simple local rules of interaction among the individuals. However, very little is known about the nature of such interaction, so that models and theories mostly rely on a prioristic assumptions. By reconstructing the three-dimensional position of individual birds in airborne flocks of a few thousand members, we show that the interaction does not depend on the metric distance, as most current models and theory assume, but rather on the topological distance. How did they do that? Well, to do that, they actually filmed real flocks in a specific area of Rome, which corresponds to the train station, the main train station in Rome. And, this is the region, the place in Rome where most of the flocks can be observed. And even in the UK, they know that indeed, there is this nice documentary of BBC called The Swarms, Nature and Tribal Invasions. And what you see here is precisely the area of the central station in Rome and these beautiful and mesmerizing flocks. So this is the map of Rome. This is the station, it's called Termini Station. Okay, here below you can see the Colosseum. This is St. Peter Cathedral, the famous columns. This is Villa Borghese. And they grew up outside of this map, in a gloomy, suburb of the city. This is the square in front of the train station. Okay, it's called Piazza dei Cinquecento. This is the entrance of the station. This is a bus station. Here you can see some trees, okay? But there are many more trees on the right-hand side of the picture, which is outside of the photo. And these trees, especially in the winter, during the migration of starlings, are completely packed with birds. And it's even frightening because, it seems like the living trees of the Sleeping Beauty. So Parisi managed to find this spot and to place cameras on the very roof of the Termini station. And that's one of the impressive part of this work, because I don't know how we managed to do that. And then using a rather sophisticated synchronization method that was developed indeed by my friend Michele together with Nicola Cabibbo, they managed to reconstruct, to film the birds, the flocks from different angles and reconstruct the three-dimensional structure of the flock. This is very complicated because in order to do that, each bird inside the flock has to be mapped to each bird from a different angle. So here you see, for instance, two images of the same flock from different angles. And in order to reconstruct the three-dimensional structure, they have to map each and every bird of both images. So here, in this example, they only have marked 5 of them so that you can see essentially how they would look like from different perspectives. These are an example of these three-dimensional reconstructions, again, from different angles. So with this data in hand, what they managed to do is what nobody else had done before, namely to look inside the flock. Okay, and while looking inside the flock, they observe something striking. For instance, what you see here is a density, angular density map of the first and the 10th neighbor. Okay, given like a specific central bird to be taken as the center. And here you can see that the two distributions differ substantially for their anisotropy. So whereas the angular distribution of the first neighbor is very anisotropic and is mostly localized along this equator, on the other hand, the 10 neighbors instead is the distribution of the 10 neighbors is much more isotropic. Okay, it's possible to aggregate this data into a single measure, a single anisotropy parameter that goes from 1 to 0, 1 being fully completely anisotropic and 0 completely isotropic. And as you can see here, this data do decay from a maximal anisotropy to an anisotropy which is roughly 1/3, and eventually plateaus to this value in correspondence to the 6th or 7th neighbor. Okay, now the different data points here correspond to different flocks. These different flocks have different densities. So what you see here is the average distance of the first neighbor. And the fact that the data already collapse on themselves, regardless the density of the flocks, is already an indication that the topological mechanism might in fact be the right one. But to make sure, what they did was a very simple reasoning, which is also very interesting. So let's call R sub n the distance of the 10th of the nth neighbor, and let's call instead R sub 1 the distance of the first neighbor. Okay. Now, because the number of particles, the number of birds, let's say in the flock scales like the volume of the flock, this means also that the distance of the nth neighbor is proportional to the distance of the first neighbor times n to the power 1/3. But this relation also somehow establishes a connection between the metric range and the topological range, which is this one. So the metric range RC is proportional to the distance of the first neighbor times the topological range to the power 1/3. And this simple equation can actually be used in order to understand whether the interaction is topological or metric. Indeed, in the case of a metric interaction, this RC, the metric range, is constant. And this implies that the distance of the first neighbor scales like the topological range to the power -1/3. On the other hand, in the case of topological interaction, is the topological range to be constant. And so this implies that the distance of the first neighbor scales like the metric range to the linear power. Okay, and these two hypotheses can be verified, can be compared with experiments, and this is the result. As you can see, the linear correlation between the metric range and the distance of the first neighbor is very evident. On the other hand, there is not much correlation between nc to the power of -1/3 with respect to the distance of the first neighbor. So this means that at least the flock of starlings do have topological interactions, unlike most models of the time used to say. This is my account for the contribution of the Parisi to our understanding of flocking. And I would like to conclude with this video that shows what happened in Rome on the 5th October 2001.
Mm-hmm.
Thank you very much.
Thanks a lot, Luca, for this very nice talk. Does anyone have any questions for Luca?
I'm curious, have there been further field campaigns done, experiments to maybe in other types of species, fish, for instance, to see if this to see the scaling that you just showed?
So there are experiments there. I mean, I'm not super updated about the literature. I know, for instance, that in Delft, the group of Daniel Tam is collaborating with the Blijdorp Zoo, where there are a school of fish as an example of schooling behavior. And they've been trying to do more or less the same thing, and namely do three-dimensional imaging of these fish. In this case, the environment is a bit more controlled, essentially, because the fish are inside the tank, and they can also use special surfaces in order to calibrate the recordings and so on. And I'm not quite sure about what is the outcome of this research yet. I mean, in fact, I spoke with Daniel not that long ago, and he told me that there has been a stop because of the COVID and all the restrictions and so on. There are other experiments with insects, for instance, where it's possible. It's a bit easier to visualize them and count them, again, because it's more controlled environment. And in this case, it's a bit different. But somehow different animals, have different ways of interacting. And for instance, while birds rely a lot on vision, okay, because they have a very powerful vision. On the other hand, insects rely mostly on chemistry, okay, because they tend to follow each other, pheromones track and so on. Not completely sure about fish. I suspect that hydrodynamics also play a role there. But generally speaking, there is no reason to expect that the law, this type of scaling law that applies to birds, also applies to other animals.
Yeah, I understand. Thanks.
Yeah.
Peter, you want to ask a question?
Yeah, very nice presentation, Luca. Thanks very much. I had also a question in the line that Dan was asking, but more about the theoretical follow-up. So you know that the Vichek model is, of course, extremely popular or famous still, and is being used all over the place. But has there been additions to this model to take into account this topological metric?
Yeah. So there are lots of different variants. Mm-hmm. In fact, the paper, this 2007 paper with these experiments also then contains some numerical simulations, which is essentially the Vichek model, but in 3D, because the original Vichek model is two-dimensional with topological interactions. And they use this simulation to argue that, for instance, this topological interaction can maintain the cohesion of the flock, okay, without the need of specific attractive interactions. And there are many other variants of that. There are many other variants of these models, which includes different type of interactions, although what is missing here, I mean, so that there is an abundance of different theoretical models. One thing that is really missing in this field is, a set of very precise comparison between theory and experiments. In fact, this paper of Parisi and the paper that came out after that from the same collaboration are possibly the only papers where people really try to quantitatively compare theory and data, which is something that typically does not happen. Okay. And now more recently, and in fact, I'm also working on that, because after the advent of machine learning, I mean, various people are trying to think about using machine learning as a way to sort of mimic the brain of these animals and see whether it's possible to shed more light on the way they interact.
Okay. Yeah. Thanks for the elaboration.
Okay. Well, thanks a lot, Luca, for this amazing talk. Let's all and we move on to our last speaker, but not the least, Dan. 1 second, I'll give you composed, right? Should be
okay. Let's see if I can share my screen. There we are.
Yes, you can try to make it full screen.
Yeah, you can see it full screen.
Yeah, we can also see your notes. just so you know.
Okay.
Yeah, it's not just a presentation. Hence your next slide. And
Okay, let me see how I can change that.
Apparently the display settings.
What's that? Display settings.
Display settings. So I had this problem in
Just duplicate slideshow, probably.
yeah, I think so.
Or this one. How's that look?
That one works. Yes. Okay.
Yes.
So it's a pleasure to have Dan Cromlin. He's a professor at the Department of Mathematics at the University of Amsterdam. And he has made a lot of contributions to stochastic systems, climate models, rare event simulation, multi-scale modeling, and many other things. And he's now going to speak about Klaus Hasselmann and stochastic modeling of climate. Please go ahead.
Yeah, okay, thanks, Jay. I'm indeed going to talk about Klaus Hasselmann. When I was preparing for this, I realized that I should also say something about Manabe, Suki Manabe, being, of course, the third winner of the Nobel Prize, and it's related, right? So Manabe and Hasselmann both worked on climate science, climate modeling, climate change, and this is reflected, of course, in the recognition. So this is a quote that I show here from the website of the Nobel Prize Foundation. So they received the prize for the physical modeling of the Earth's climate, quantifying variability and reliably predicting global warming. So it's not only about Hasselmann, but also a little bit about Manabe. Now to introduce some of the work that they both did, I will show a couple of slides about some very basic concepts of climate modeling, some ideas that go back a long time, fearing that maybe not for everyone in this audience, this is something you see frequently. So arguably the simplest model that you can think of is what's called an energy balance model, and it's just a model that's looks at the balance between the incoming and outgoing radiation on Earth. So there's the incoming radiation from the sun, that's shortwave radiation. It's absorbed by the Earth, and then the Earth heats up because of that. It reaches a certain temperature, and there's as a result of that, there's outgoing radiation at longer wavelengths, and that's just the Stefan Boltzmann law that has been known for a long time. Now, in this very simple setting, one thing you can account for, and I've indicated that here, is that the Earth's surface is not fully absorbing. So there's a partial reflection of solar radiation, for instance. You have ice caps. Of course, a lot of the radiation is just reflected back, and that effect is sort of summarized in what's called the surface albedo. And if you take that into account, then this very simple energy balance sort of setup, where there is no spatial variation in whatever direction, and there is no atmosphere taken into account. If you compute that, you reach a surface temperature of the Earth of about minus 15 degrees. Right? So clearly way off. Now, it's in particular the absence of the atmosphere and its constituents, right? The gases in that make up the atmosphere that makes a big difference here, and that is something that has been known already for a long time. It goes back to Arrhenius already in the late 19th century. So he made a detailed study, and this is the paper that he published on that a long time ago, looking at what happens to the temperature of at the Earth's surface if you account for absorption and emission by gases in the atmosphere, right? And the different kind of properties when it comes to absorption and emission that different constituents of the atmosphere have. For instance, water vapor and carbon dioxide. So taking that into account, things change dramatically. So the temperature, right, so again, looking at still at a what I call zero-dimensional model, so no spatial extent, but there is now accounting for the effect of greenhouse gases, and by that computation, temperature should be on the order of 34 degrees Celsius, so quite warm, much warmer, of course, than what we really see. Not only did Arrhenius make computation of temperature, but also of climate sensitivity, and of course that is very important now in the context of climate change. Climate sensitivity is sort of summarized here as the increase in temperature that you get by doubling the concentration of atmospheric CO2. Right? And Arrhenius came to a number of 6 degrees as climate sensitivity. Okay, now this brings us to Manabe. So I mentioned, so it's these simple concepts that I just discussed are zero-dimensional models. There is no spatial extent, not in a horizontal direction, so not north, south, east, west, or even vertically, so going up from the surface. And what Manabe did in a paper from the late 60s with Wetherald, so 2 authors, they looked at what's now called an atmospheric column model. So it's a model, a one-dimensional model that's for the vertical structure of the atmosphere. So the vertical structure of the temperature and moisture, so humidity, water vapor, and greenhouse gases like CO2 and methane. Right? And in that model, there's a lot more that's captured in terms of the physics, right? There's radiative transfer, but there's also vertical transport, vertical motion of air. That's called convection, right? There's heating at the surface, the air warms up, and part of it sort of rises. So that's convection, and as that air rises up, it cools down, and then at some point, part of the water vapor that is in that air is going to condensate, and that creates latent heat release, and that sort of warms up the air locally. Right. So all these different physical properties were taken into account. He was the first to do this, to develop this model. It wasn't. He had to solve this numerically, and came at these surprisingly accurate, if you think of the simplicity of the model in a way. It came to these numbers of surface temperature about 18 degrees, right? So again, I should mention there's no accounting for north or south, whether you're close to the equator or to the poles. That's not accounted for here, nor seasonal effects, but on average about 18 degrees. So that's in a realistic range. And also climate sensitivity. So what happens again upon doubling CO2 amounts, climate sensitivity of 2.3 degrees. And that's very much still in close to the range of what contemporary, so the state-of-the-art climate models predicts for climate sensitivity, which is in the range of 2.5 to 4 degrees Celsius. Okay, now this is still one-dimensional. In a next paper, a number of years later, 1975, he made a step from a one-dimensional model with only vertical extent to a fully three-dimensional model. So also horizontal motion of air. So it's right. The atmospheric circulation is being captured by that. So on the right, you see a figure. It's showing right from that paper, showing all the different components and how they interact. So it gets much more complicated. And in this paper, they studied again the effects of increasing CO2 concentration in the atmosphere, but now with a fully three-dimensional model. And I think the climate sensitivity that they got out of that is a little higher. I thought it was 2.9 degrees Celsius. So again, that is really in the range of what are still the best estimates today. And one other interesting aspect of this is that it shows very clearly, and that is also something that can be verified, of course, with observations, that if you increase CO2, so the lower part of the atmosphere gets warmer, but the higher parts in the stratosphere cools down. And that's very different from what you get if just the solar radiation itself would become a little bit stronger, because then you would expect to see a warming all over the vertical range. Okay, now in this three-dimensional model, of course, a lot more is happening, and there's variations in circulation on many different space and time scales. And I'm bringing to this next figure, where you see that the climate system is really a multi-scale dynamical system. So it changes in time, but it has many different features and processes that are relevant on different space and time scales. What you see here on the horizontal is the spatial range going from meters up to the planetary scales that are thousands of kilometers. In the vertical, processes that evolve on a time scale of even seconds, right? Really small scale turbulence, all the way up to years and decades and centuries, right? And there are different climate phenomena that are associated with that you can see here. Okay, now it's obviously very difficult to capture all these skills. It's numerically not feasible to compute with all of those skills, and that brings me to Hasselmann, because he came up with the idea to consider a stochastic description of the climate system, where the atmosphere acts as noise. That's in this paper from the 70s, and you can wonder, well, why would you consider the atmosphere as noise? Well, of course, that was also in part motivated by insights developed a bit earlier in the 60s by Ed Lorenz, who, of course, famously discovered that the atmosphere behaves chaotically. It's extremely sensitive to initial conditions. And in that sense, right, this chaotic nature is a motivation to say, well, you can consider what happens in the atmosphere as being, in some sense, random or noisy. Like the equations that you see here, of course, from the famous model from 1963 that Lorenz formulated, and it gives rise to this butterfly-shaped attractor that I show here on the right. Okay, now making the step from a deterministic description to a stochastic one that's very non-trivial, right? So you go from coupled deterministic ordinary differential equations for fast variables, which are the atmosphere, and slow variables that are all the other parts of the climate system, like oceans and ice caps and more, and to make the step to an effective description in terms of stochastic ordinary differential equations. That is conceptually, mathematically, a very non-trivial step, and this has led to a lot of work where people have tried to make sense of this mathematically and to put this on a rigorous foundation. So I have a couple of slides to say a bit more about that. Right, so this is about more the math context of what some people have come to call Hasselmann's program. So this stochastic description of the climate system. Right, so schematically here, two coupled nonlinear differential equations for slow and fast variables. Right, of course these are vector valued because they typically represent a lot of different variables. And the important assumption here is that there is time scale separation between slow and fast. Right, so it's this epsilon parameter here. And then, so in somewhat technical terms, you can prove on certain assumptions, certain conditions, that the behavior of the slow degrees of freedom converge to this effective or average equation that I show here at the bottom. So that is on what are called order 1 timescales. This is a good approximation, but then if you go to even longer timescales, I mean, you get to see deviations from this average dynamics, and then you go to this effective stochastic equation, right? So this is sort of the in essence, the idea that Hasselmann also put forward, you get an effective stochastic description of the slow degrees of freedom. And this is sometimes referred to as the sort of the homogenized equation that comes from this set that I show here at the top. Okay, so there are, of course, all kinds of math issues, more technical issues that people have delved into. They're important to think about. So you get convergence, is it strong or weak convergence, what timescales, and so on. Certain assumptions about how fast the fast part of the system decorrelates and mixes, and whether it's ergodic or not. So these are mathematically very tricky questions that must be answered, and not all of them have been answered so far, right? And I show here a bunch of papers and names of people who have worked on these on various aspects of these problems over several decades. One more aspect. So I mentioned this assumption of timescale separation between atmosphere and ocean, but in practice and reality, there's no real clear scale gap that we see between atmospheric motion and ocean circulation. Right? So in practice, you don't have this clear gap. So these ideas of averaging and homogenization become difficult then, because they do rely on this assumption of timescale separation. Then you have to go over to other ideas, and there's this the framework of that was developed by Mori and Swansig. That can be a way to go forward on this, and what you get out of that is an effective model that's essentially a generalized Langevin equation, but now with memory. Right? So there's a memory kernel. It's this part in the middle. That comes into play then. So it's a more complicated system. It's also very difficult to implement this or to carry this through. And there's a lot of research ongoing to try to push this forward. Okay, I'm start to run out of time, so let me move on and leave the math questions behind, even though, of course, they're very interesting. So let's go back to Hasselmann, right? So the paper title that I showed earlier was Stochastic Climate Models Part 1. Just about 1 year later or 2 years later, there was Part 2, where this idea was effectively put to use to try and understand low frequency variability of the upper layer of the ocean. And what you see here on the figure at the bottom right is the power spectrum comparing the theoretical spectrum that comes from this effective stochastic model. That's sort of the smooth curve that you see here compared to observations, observational data at a particular point. And you see that it's a fairly good match in the sense that you do get to see this red power spectrum that is predicted by the stochastic model. Right. So what's interesting here, of course, is that what it shows is that you get low frequency variability in the ocean due to high frequency variability from the atmosphere. Right. So it transfers from the high frequency to the low frequency domain here. Okay, now Hasselmann proposes, but then moved on to other topics, and this is connecting really to climate change studies. What he developed was the idea later on of fingerprinting, and that's a sort of methodology to detect a signal of climate change among the short-term variability or the noise that you get from the natural variability of the climate system. And the first papers, there's a series of papers on this that he wrote, but the first one is the one that I show here. From 79, and so the key idea there was to not look at what's happening at data at a particular spatial location over a long time, but also to look especially at data of spatial patterns, and to use that, right, to effectively treat this as a pattern detection problem, as he puts it himself, to detect climate change signal. And that brings me to my last slide. So this idea really made it big and has been adopted by many, many people for the whole sort of field of study of attribution and detection of climate change. And so the contribution of Hasselmann to this is highlighted again in his recent paper from Nature Climate Change a few years ago, where one of these three key events is really the idea put forward by Hasselmann that I showed on the previous slides. And it's now, as you see here, widely regarded as the first serious effort to provide a framework for identifying human-caused warming signal. So obviously a key contribution by Hasselmann to understanding and studying climate change. Okay, let me leave it at that. I'm running out of time, so thanks.
Thank you.
Yes, thank you a lot, Dan, for this nice talk. Does anyone have any questions? Well, I can definitely ask a political question. So, so the works you showed of Manabe always had the same co-worker, and yeah, when I was also looking at his work for this, I was just wondering, what about the co-worker?
You mean the so that's the weather odds?
Yes.
Yeah, that's on those particular papers. I mean, Manabe has many more papers the important contributions that I haven't highlighted here. That's he made with either on his own or with other co-authors. But it's true. I mean, on these two particular papers, so the weather odds is happens to be a co-author.
Yeah. Okay.
So yeah, I'm not sure whether I haven't looked into what weather odds has done more and
okay.
Yeah.
Does anyone have any other question? Or? No. Okay.
Maybe I do. So
yeah. Okay.
So do you actually know what, like, when you were talking about the Morris-Swansea stuff? Did they actually use the Morris-Swansea formalism at some point in these works, or it's just you were just trying to create a relation between the stochastic and deterministic models?
Yeah, you mean whether Hasselmann used this?
Yeah, basically.
No, not no, I don't, not that I know of. No, because he also moved on to from this idea of stochastic modeling to other topics. Now the idea to look at the Morris-Swansea framework is much more recent. So other people have taken it up and
this is what I was thinking. Yes.
Yeah. So, for instance, I mean, this idea has not only been used, of course, in context of climate modeling, more generally for all kinds of multi-scale dynamical systems, and right in fluid dynamics, turbulence studies, but also elsewhere. And so, in particular, for fluid dynamics, Alexander Chorin in Berkeley has done quite some work on that about 20 years ago. But now, with Hasselmann himself, I don't think he's looked into that or published on that. Not that I know of.
But the current climate models, so they build up on Hasselmann's work, or is it more a different formulation? Or?
Well, no and yes. The main thrust of in climate research using and developing numerical models is still to go for ever higher resolution, more complexities, or bigger and bigger and bigger models. But there's also now a strain of research that's making use of not representing the atmosphere in full in a stochastic manner, but representing sort of small-scale processes in the atmosphere in a stochastic manner. Right? So that's the idea of stochastic parameterization. So sort of augmenting the atmosphere model to represent whatever cannot be resolved in the atmosphere model, and that is something that is now being used, for instance, in weather forecasting, but also in climate models. So that's in indirectly, I guess, does work does build on these ideas by Hasselman.
Thanks.
But I think there's more potential to it than that.
Okay, thanks a lot then. We're definitely much over the time that we were supposed to have this seminar. So we stop here. We just, thanks a lot to everyone for showing up, and let's just give another round of applause to Dan and all the other speakers.
Thank you, Jay, for organizing this. Very nice.
Thanks.
Yeah, thanks, Jay. Bye, everybody.